Hey everyone, welcome to today's webinar. Thanks for joining us. My name's Megan. I am a product marketer here at Cockroach Labs, and I'm here with Joel. Do you want to just introduce yourself?
Hi, I'm Joel. I'm a site reliability engineer at Cockroach Labs.
Cool, and today we're going to do a live Q&A about Kubernetes. So some of you sent in questions prior to the webinar, and we're going to go over those questions. And then if we have extra time later on, you can also submit additional questions in the Q&A feature at the bottom of your screen. And then after we finish the Q&A section, we're going to present a video that is a talk that was given by Alex Robinson at last year's KubeCon. So obviously we're all getting really excited about KubeCon here at Cockroach Labs. And so basically Alex Robinson is a Kubernetes expert who did a lot of research on CockroachDB and Kubernetes. He initiated a lot of this research. So we're excited to present his talk from last year.
Yeah,
okay, let's get started, Joel. So we had a few questions come in before the webinar. And the first one is about virtual networking. So it says virtual networking and secure cross-region communication, like is that an option?
Yeah, so I should note that if you run CockroachDB in secure mode, we do rely on fully encrypted in-transit communication between all of your CockroachDB pods, both within a single region and multi-region.
Okay.
If you want to expand this beyond CockroachDB itself to any arbitrary application, your data won't be encrypted by default, but you could use a service mesh such as Istio, which will provide you in-transit encryption. And this also works either single region or multi-region across different Kubernetes clusters.
Cool.
Yeah, and then region local container registries, what you mentioned. Yeah, there's many different cloud providers provide that feature just out of the box, such as AWS and Google Cloud, Azure. They all will support uploading the same container image to different regions.
Okay.
Just in case you wanted to host your containers in different regions in case one wasn't available.
Cool.
Yeah.
Thanks. Let's move on to the next question. So this person wants to know some details on cloud service providers. So and how we're dealing with multi-cloud problems.
Yeah, so I don't think there's great support for multi-cloud. Google released a project recently called Anthos, which I'm still sort of figuring out myself. For the Cockroach Cloud team, we rely on some tools that allow us to orchestrate different cloud providers, such as Terraform, which allows us to just define a common set of resources and then have Terraform deal with all of the API calls to different cloud providers to spin up different VMs or Kubernetes clusters. We also use a tool called Pulumi, which is like Terraform, but it sort of provides better support for interacting with cloud providers via a programming language such as Go or Python or Node.js. There's also a really interesting project called Crossplane, which is sort of the same idea as Terraform or Pulumi, but it takes on a more like Kubernetes like structure to defining resources in different cloud providers.
Cool.
But in terms of support from cloud providers themselves, I think there's still a lot of ways to go.
Cool, that's super helpful. We had a few questions come in about multi-region Kubernetes clusters. So some people were wondering, are the Kubernetes clusters cross-region or are they separate clusters?
Yeah, so Kubernetes itself only runs in a single region, and originally it only ran in a single availability zone within a region, but that's been improved. But sort of the focus of this talk that you'll hear from Alex in a few minutes is about how you can spin up a multi-region application such as CockroachDB onto different Kubernetes clusters, one in each region, and have them all communicate together. And we also have some resources on a website. Alex made a blog last year that had like 5 different approaches to multi-region Kubernetes. We have an example in our GitHub repo where you can spin up a multi-region GKE Cockroach cluster. And so, yeah, I'd encourage you to check those out.
Yeah, definitely check those out. Those are some good resources. And then we have a question, says, how can I access the database publicly by IP? I want to access the database IP to my applications, which are running in a different cluster. Yeah, any thoughts on that question?
Yeah, so within Cockroach Cloud team, for each region, we create a service of type load balancer. And so a Kubernetes service will take all of the pods in a cluster and expose them at a single IP address. And if this service is of type load balancer, then in different cloud providers such as AWS, Azure, or Google Cloud, it will create an actual layer for load balancer. And then your external applications can reach CockroachDB via this load balancer. It still means that you have one load balancer per region. So if you have a multi-region application, I think my recommended way would be to, for each region of your application, point it to the load balancer that is nearest to the application. Mm-hmm. Now, if you're running on AWS and you're using Route 53, you could use something called latency-based routing within Route 53. So you will have a single URL for all of your load balancers, and then you'll have a different record set for that same URL, and you can rely on Route 53 to basically route any DNS request from your application to the load balancer that is nearest to it.
Cool.
In terms of support from other cloud providers, I think Google is sort of lacking in this regard right now. Not to call them out or anything. Yeah. I don't know about other cloud providers at the moment. So I think the easiest way is just to configure your applications per region.
Mm-hmm. Okay, that makes sense. And then we have an additional question about Gorm. So it says, how close are you to full level support for Gorm? I would love to deploy a multi-region Kubernetes cluster with Cockroach and Golang using Gorm.
Yeah, so I know we have an app dev team that is actively working on this support. I don't know the details, but I'd encourage you to either ask in the forum or our new community Slack that we've created at cockroachdb.slack.com.
Yeah, that's what it is. Yeah, definitely ask that question there. We can also reach out to you afterwards with the answer from our app dev team, who could definitely answer that question. Cool. Let me see if we had any other questions come in while we were talking. It doesn't look like we had any more questions come in. So I think we're gonna switch over now to Alex Robinson's talk, and just hang tight while we switch over the screen.
Morning, thanks for the introduction, and let's get right into it. My name is Alex, and I'm going to be talking, as you probably assume, about running a distributed system across Kubernetes clusters. And if any of you have run Kubernetes clusters recently, over the last year or two, you probably found that it's a pretty nice way to run your distributed applications. It gives you a whole lot of great things and makes it easy to run even pretty complicated applications like a distributed system. But if you tried doing this a few years ago, you'd know that Kubernetes has come a very long way over the last 2 to 3 years. If you'd wanted to run a system 3 years ago, you would have had a really tough time running anything that has data in it. You're missing out on features like volume provisioning and stateful sets. There weren't any multi-zone clusters until a couple of years ago. As someone who tries to make it easy for other people to run my application on Kubernetes, meaning I want to make it so that other people can run Cockroach on Kubernetes, innovations like Helm charts and operators have been great developments in the community as well. And as an end user using Kubernetes, it's great that there are more and more managed Kubernetes services these days that make it so that you don't have to run your own cluster. However, things haven't really improved if you want your service to span across multiple regions or multiple Kubernetes clusters. Very little community developments have happened since the creation of Kubernetes in order to make this a better experience. There have been some early efforts, such as the Kubernetes project, that was Kubernetes without a K, and the recent Federation V2 project is still ongoing. But nothing has yet solved the problem of trying to run a distributed system that spans multiple clusters. It's still a very hard experience that isn't really documented at all. You need a lot of expertise to kind of even know where to get started. You might ask why you would even want to run a system across multiple regions, though. Maybe there's a reason that this work hasn't been done by the community. And I'd argue there are two big reasons, and maybe some other smaller ones as well. The biggest reason is user latency. The further away your service is from your users, the longer it's going to take for them to get their responses back from your service. And the faster your service is, usually the more people will engage with it, the more time they'll spend with it, and the happier they'll be. This is especially critical if you're running a global service that has users all over the world. If you don't have any instances of your service near them, they're going to have to wait hundreds of milliseconds to get responses back from the service. So this is a very strong reason for wanting to run whatever you're running across multiple regions. As well, fault tolerance becomes very important. You want your application to continue running even if an entire data center or an entire region of data centers goes offline for some terrible reason. So in this case, if the data center over in California goes down, users on the West Coast might have to wait a little longer for their responses, but they'll still be able to use your service because of the other replicas that are stood up on the other parts of the country. And there might be bureaucratic reasons for wanting to run a system across multiple regions. There are many laws in many countries now around where you're allowed to store users' data without their permission. So if you might have to store the data from users in China, and you might need to store the data from users in Russia. And having a system that spans multiple regions enables you to do that. If you only have a data center in the US, then you're going to have a tough time. And so for the bulk of today, I want to talk about the practical experience of running a distributed system across multiple Kubernetes clusters and what it's really like. And we're going to cover why it's hard, what kinds of detailed information about Kubernetes or about your distributed system you should know before you get started. And then we're going to look at some solutions that we've put into production in various environments and seen work well for us. And just so that you know where I'm coming from, my experience with Kubernetes it goes back quite a while. I worked directly on Kubernetes and the Google Kubernetes engine from mid-2014 for about 2 years. I was part of the team that launched GKE in the first place. And while I was there, I worked on cloud provider integration, networking, logging, monitoring, a whole bunch of things in Kubernetes and in the managed service as well. And since then, I joined Cockroach Labs to work on CockroachDB. And in addition to working on the performance and reliability of the database itself, I also have worked on all container-related efforts for us. So that's meant creating multiple configurations for different orchestration systems, helping people run them in all sorts of different environments, whether it's single zone or multi-region. And also, even though my goal is to create configurations that can be universally used by pretty much anyone, there will still be some users at the edges who need to do things their own way for one reason or another. And I also end up helping them with their more custom setups. So my goal is to standardize things, but I also understand that not everyone can use the standard solutions and get to see some of the edge case solutions as well. And so the question of why it's hard is something that many people might not even think to ask. I've had a number of conversations with folks where they'll assume that since CockroachDB runs really well across regions, and because Kubernetes makes it really easy to run CockroachDB, that it's just naturally going to be easy to run CockroachDB across multiple Kubernetes clusters spanning regions. But in fact, it's not easy at all. It's significantly harder than running Cockroach in a single cluster. And some of you might have noticed that so far I've been using the terms multi-region and multi-cluster essentially interchangeably. And that's because Kubernetes is not designed to have a single cluster span multiple regions on the wide area network. For quite a while, it wasn't even recommended to have a single cluster that spanned multiple availability zones within a region. The community fought for that, so that's now it's now a recommended configuration. It's called a multi-zone cluster. But trying to run a single Kubernetes cluster that spans regions is definitely at your own risk. It's not something anyone I've ever known would recommend. And so I'm going to keep using these terms mostly interchangeably. But what this means is that if you want to run something like CockroachDB across multiple regions, you are necessarily going to have multiple Kubernetes clusters, at least one in each of those regions. And to better understand the problem of setting up a system like CockroachDB across multiple regions, it helps to understand what does a system like Cockroach or any other stateful service need to run reliably in the first place, because we're going to have to provide any of those things. And today we will be using CockroachDB as our example. It's by far the system that I'm most familiar with running in Kubernetes because I've had to do it for a couple of years now. And CockroachDB, for anyone who isn't familiar with it, is an open source distributed SQL database. Your applications can talk to it as if it was Postgres, but all of your tables and all of your data is going to be sorted by key and split into chunks. And those chunks, called ranges, are then replicated across the cluster. So that there are multiple copies of them. As nodes get added to or removed from the cluster, all those ranges will get automatically rebalanced. And we use a consensus protocol to ensure consistency and strong levels of isolation between transactions. And when you do want to run Cockroach across multiple regions, we provide this feature known as locality, where you can tell each node where it's running, and it'll use that information to try and distribute your data across as many fault domains as possible. Or you can tell it to put some of your data only in certain localities if there are regulatory or performance reasons for doing so. But CockroachDB is one of the easiest stateful systems that you can run in Kubernetes. It's very, very flexible and forgiving. All of the nodes are the same as each other in a sense. There aren't any special binaries, there aren't any special roles. Clients can talk to any of the nodes. All of the nodes serve exactly the same role in the cluster. But Cockroach requires roughly 3 things in order to run reliably. Every Cockroach node has to have some sort of persistent storage that will survive across restarts of that process. Each node has to have a network address that it can advertise to the other nodes so that they can talk to each other reliably. And that address ideally should survive restarts so that you're not always changing addresses. And each node can communicate directly with each other node. So the second point here is you can kind of be flexible about. CockroachDB actually will work if your nodes are changing network addresses. But this is something that most stateful systems need, and so we'll leave it in here for the sake of details. So this is a fairly generalizable list. There are a lot of stateful systems that need these things. And Kubernetes provides these all very well within the context of a single cluster. You might have heard of the controller known as a stateful set, and it was designed to provide exactly these 3 things. The Kubernetes stateful set gives each node its own disk, or multiple disks. It gives each node its own address. And Kubernetes itself guarantees that all pods can communicate directly with each other. But across multiple Kubernetes clusters, we definitely lose number 2. There's no cross-cluster addressing system. And we often lose number 3. It's often not set up such that a pod in one cluster can talk directly to a pod in another cluster. That's what we might call pod-to-pod connectivity later in this talk. And so the core problem of running a multi-region system all comes down to the networking. You might not have pod-to-pod communication across clusters. You might have to communicate across separate private networks in order to talk from one cluster to another. For example, if you're on AWS, each Kubernetes cluster is going to be in a different region and thus in a different VPC. So you're going to have to connect those together with some sort of VPC peering or a VPN. And this is going to be even more true if you're spanning multiple cloud providers. And finally, we also need a persistent address that works both within and between the clusters. We could weaken that last point to have 2 separate addresses. So one that works within the local cluster and one that works between them. And that'll be fine as long as your system is sophisticated enough to handle having separate addresses like that. So that will work for CockroachDB, but wouldn't work quite so well for many other distributed systems that assume just one address. So networking is the problem. And the question is, why is it a problem? What's the deal with it? How come this multi-cluster case just has no support? And if we go back in time, Kubernetes specifies a list of requirements from the network. So each pod running in a cluster has to be given its own IP address. And that IP address has to be something that the pod itself sees inside its container. And it's the same IP address that other pods in the network see it as. So a pod doing like an IF config should see the same IP address as the pod that it sends a network packet to. And all pods can communicate directly with each other without any form of NAT. So no network address translation should be needed. And this is very different from how, say, Docker was doing things at the time, and even how it typically does things now. So Docker would typically give each container on a node its own private IP address, but that private IP address only works on that one machine. And then some sort of NAT is needed for cross-host communication. This is also different from how networking worked inside Google for their Borg system, where each pod just shared the host machine's IP address and was given its own set of dynamically allocated ports. This was a pretty revolutionary idea. And so they laid down these requirements very firmly, saying like a Kubernetes cluster needs to have these things, otherwise it's not a compliant Kubernetes cluster. But this posed a real problem because we want to run a lot of pods on each machine, but traditional networks only allocate 1 or 2 IP addresses to each host in this cluster, or to each host in their network. We needed some way of creating new IP addresses for each of the pods on these machines. And it turns out that there have been a lot of solutions dreamt up over the last few years to satisfy those requirements. There are dozens of solutions out there. And while you can group them into a few classes, they all have details that differ from each other. And so you have tons of different solutions out there, all of which are being used, which means that you can't really rely on implementation details to be true in any given Kubernetes cluster. Like a cluster that works on GCE might be working a little differently than one that runs on AWS versus one that runs on-prem using a particular piece of networking software versus one that's running in DigitalOcean using some other networking software. And because the multi-cluster scenario is left completely unspecified, all those little implementation details of the different networking solutions become really critical because they aren't trying to provide any sort of guarantee about how multi-cluster works. So the way that multi-cluster works is completely left up to the implementation details. It's kind of when you're running a C program and you hit some undefined behavior, maybe it'll work for you on one C compiler and one architecture, and maybe it won't work for you on the other C compiler and the other machine architecture. So this is a really bad combination that just means using multi-cluster is a bit of a minefield because you won't know exactly how the network underneath works unless you know exactly which network you're running on. And there are a lot of networking solutions out there. These are just a few of them. And again, they all work differently. So there's only so much in common that you can depend upon them. And that means that any solution you end up using may have to depend on your networking provider, which is really frustrating from my perspective, where I'm trying to make configurations that everyone can use. It's not something that's very easy to do when everyone is using different networking providers. And so we can kind of group them into 3 categories, where some of them do enable direct pod-to-pod communication across clusters out of the box. GKE has always done this. Amazon's Elastic Kubernetes service has started doing this as of earlier this year. They changed their networking model a bit to make it possible. I don't know if this was directly their goal, but their change to using elastic network interfaces and floating IP addresses made this possible. And others don't have it on by default, but make it fairly easy to enable. So the Azure Kubernetes service, you have to turn on their advanced networking mode to make this possible. And there's a overlay network provider called Cilium, which offers a simple feature known as the cluster mesh, which makes it really easy to turn this on, even if it's not there by default. But in many other networking solutions, it can be quite difficult. And this is especially prevalent for on-prem clusters or for situations where you want to span multiple clouds. So this is a tough problem. And there's a wide space of networking providers being used under the hood, so it's unlikely that there's one single solution. But let's take a look at some of the options for what we can do. And unfortunately, all of the options have one problem or another. And I did most of my work on this in the first half of the year. So it's possible that some development has happened here that I haven't heard about that gets rid of some of these cons. But as far as I've seen, I've been keeping up and trying to play with things every once in a while. And I haven't seen a great solution that's fully mature yet. Work is being done on it, though, which we'll see later. And so, some of the solutions don't work in certain environments. Some of them, break very easily if the operator of the clusters isn't very careful about what they're doing. Some of them use a slower data path, and so you're going to have a less performance system if you use them. Others don't work well with TLS certificates, so you might have to run your cluster in what we at Cockroach call an insecure mode, where you aren't relying on certificates to secure all communication between nodes. Yet other solutions rely on an immature or very complex system that isn't quite ready to be used in production yet, even if it's on the right track. And those systems in particular, the new systems being built, have been improving throughout the course of the year. So I do think there's a lot of promise in the future in the next year or so for good solutions that you can depend on for this. And again, my perspective on this is likely different from many of yours, just because my goal is to help customers run Cockroach across their diverse Kubernetes environments. If my job was to just get this working within a single stable environment, I could pretty easily identify which one of the many solutions works well for it, and then just go with it and be done. So this is made a little tougher by the fact that I'm trying to come up with some sort of universal set of instructions. And note that for most of these solutions, I'm assuming that in each Kubernetes cluster, you're just going to run a stateful set, and then you're doing something to like connect their networks together. So then if you wanted to scale up the nodes that you have running in one Kubernetes cluster, you would just scale the stateful set that's running there, and vice versa if you wanted to scale the nodes running in one of your other clusters. There's only one exception to that, which we will look at first. So let's look at that one. So one way to do this is to pretend that you're not really using Kubernetes at all. So Kubernetes allows you to statically place pods onto specific nodes, or you can use what's known as a daemon set, which just puts one pod on every node. And then you can use the host network option in the config file, the Kubernetes configuration file, to tell the pod to use the host machine's network directly. So it will use the host machine's IP address for all of its communication. This means that your pod will be using the ports directly on the host's network. So you can't have more than one Cockroach pod on that machine, because you're going to run into port conflicts if you do. But this means that you can use that host's IP address to communicate between nodes in different clusters. And so as long as you've set up your network such that your VMs or your physical machines in the different clusters can directly talk to each other, and Cockroach pods on those machines will be able to directly talk to each other. And in order to avoid changing addresses all the time and potentially like getting some sort of split brain situation, you're probably going to want to statically assign these pods to machines. So either by directly in the config file saying which host you want each pod to run on, or by using the daemon set, such that you're just always running one Cockroach instance on each machine, so that their IPs stay the same. And this is great because it works even if you don't have that pod-to-pod IP address communication between clusters, because you're just relying on the machines in each cluster having direct IP routability. And this has no moving parts, which is really nice. You don't need any sort of cross-cluster naming service. You'll just have to set up your join flags when you start nodes to include some of the machine's IP addresses. So I should clarify that when you start Cockroach and want to join a few separate nodes together into a cluster, you give each of them a join flag on the command line that says join to one or more of these addresses. And so you can specify IP addresses or DNS names. And when the Cockroach node starts up, it will try to connect to those addresses. And if it can connect to any of them, it will join into the cluster that node is connected to is a part of. And so for the join flags in the solution, we would just specify some of those machines' IP addresses that we're going to be using. And then once you set that up, you won't have to change them all the time. The big caveat with this is that it depends on your host's IP addresses not changing. So this is especially a problem on cloud providers, because if you're using a hosted solution like GKE or EKS, they do node upgrades. They upgrade the Kubernetes software on each VM by just tearing down, deleting the VM, and recreating it. And when it gets recreated, it's very likely to get a different IP address. And because we're relying on those IP addresses to stay the same, this could lead to problems. It could lead to the cluster, like a new cluster being started up, or nodes not being able to connect to the action cluster after being restarted during these upgrades. So this is something you'd have to be very careful about if you're running on one of these clouds. You might need a special upgrade process, or you might need to modify the IP addresses while this is going on. Modify the IP addresses and the join flags while this is happening. So you have to be very careful while doing this. But I have run this for a while. In test environments, and it works really well because you get high performance because the nodes are just talking directly to each other. So it performs very well. And once you set it up, you don't really have to think much about it other than during those upgrade scenarios. And you want to be really careful on GKE, which can sometimes do automatic node upgrades if you don't configure it not to. So again, be careful if you go this route, but it is pretty reliable if you put in that care up front. And there's a bit of manual work involved in editing the configuration files to put in those join IP addresses, and assuming you want to run in secure mode, to create those certificates for each IP address. But overall, this is a totally fine way of doing it. And you'll also get maybe some extra reliability by doing it this way, because any sort of dynamic movement that Kubernetes would otherwise do to move your pods around and have to detach and reattach disks just kind of becomes a non-issue because none of that's happening here. And so there are some people that would argue that they don't trust Kubernetes to run their stateful services, who would trust something like this because Kubernetes isn't really getting in the way. However, if you do want to take advantage of more of Kubernetes features like rescheduling, health checks, and all that stuff, this is a good solution that we do have some customers running in production that has worked quite well for them. It can be a little heavy to set up in the first place, but can work quite well after that. And what we do here is, we run a stateful set in each cluster, and then we create a public load balancer for each CockroachDB pod. And this is something that's really easy to do in all the major cloud providers because they all have plugins for Kubernetes that make it really easy to expose a service from within a cluster. And so we get a separate load balanced IP address for each of the Cockroach nodes. So say we have 3 Cockroach nodes in our cluster, we'll get a separate IP address for CockroachDB0, CockroachDB1, CockroachDB2. And then we have to take those addresses from the load balancers and have all the pods connect to each other using those addresses. And we create certificates for all the nodes using those addresses. And since those load balancer IPs are stable, the underlying CockroachDB pods can be deleted and recreated, moved from one node to another, and so on and so forth. And the load balanced IP addresses will always route to the correct Cockroach pod. So this is great, and we have had people using this for many months, working well for it. And this is great because it works even when you don't have that pod-to-pod communication between clusters, just like in the previous solution. Because all communication between pods that are in different clusters is going through that load balanced IP address. And it continues working even as Kubernetes hosts churn in and out of the cluster. So it avoids that problem with the previous solution, because even if nodes are being deleted and recreated all the time in the cloud, it's okay because the pods are still using the same load balanced IP address. And again, this doesn't require you to add any extra moving parts to your system other than the load balanced IPs. You don't have to run some service that allows the Cockroach pods in one cluster to be able to find the Cockroach pods in another cluster, because you just have those load balancers that are presumably being run by your cloud provider. There are some problems with this, of course, though, most particularly in how hard it is to configure, and the fact that it adds some extra overhead on the data path, so it can be a little lower performing than things like the previous solution. Because on all but the most sophisticated load balancers, when you send a packet to that load balanced IP address, the load balancer will just forward it to any random host in the other Kubernetes cluster. And then that other host is going to have to look up where the pod is actually running and forward the packet to that host where the pod is actually. Some providers are smarter, I believe the load balancer integration on Google Cloud is smart enough now that the load balancer will send the packet directly to where the pod is running. But that's not going to be true everywhere. And so you might see slightly worse performance doing this. But most importantly is that it can be a pain to have to create a new load balancer every time you want to add a new node to your cluster. If you forget to do this, which it can be very easy to do, because you might just run the kubectl scale command, and then you'll see that your new pod is working because it doesn't have this IP address already configured for it. So you have to remember to do that. And it also can be expensive to run so many load balancers. So this will again depend on the cloud, but creating this many load balancers on AWS could be quite costly. And you might not be able to do this on-prem if you don't have good load balancer integration between your Kubernetes cluster and some sort of manually run load balancer like HA Proxy. And again, setting this up requires a lot of manual config file editing and certificate creating. So you get this a pretty advanced, complex configuration to make this happen. But once you set it up, it's going to be very reliable. I haven't heard of any outages caused by this sort of configuration. Just some hiccups while adding a new node to the cluster. But that didn't affect the currently running nodes, thankfully. The next solution, which you can do, is if you have direct communication between pods in different clusters, you can just let the pods advertise their internal pod IP addresses to each other directly. And of course, as pods get deleted and recreated on a new node, they might come back up with a different IP address. But Cockroach is able to actually handle this as long as the disk is moving around with the pod. So you can just rely on Cockroach's ability to handle node addresses changing to deal with the churn that will inevitably happen as pods move around the cluster. You'll also need to set up some sort of load balancer that can be used for the join flag, because we do need the join flag to have some sort of addresses that will always be there. But that join flag doesn't get used on the data path. And so this is actually quite fast because the pods are communicating directly with each other across the different clusters. And so yeah, the pros are that this is very fast. There's no overhead on the data path at all, other than the normal Docker overhead of bringing packets into a container and back out of it again. this is very resilient to changes. You can add and remove hosts as much as you want, and this is actually really easy to maintain once you start it up. The only real caveats is that you need to have that direct pod-to-pod communication across clusters. And the biggest one is that it's hard to do this in secure mode if you want to run with TLS certificates. It's tough to do because Cockroach by default does hostname verification on certificates. And so the IP address that a pod is running at has to actually be in that signed certificate. Otherwise, other nodes won't trust it. And so we haven't tried running this in any sort of secure. We've only run it sort of as a proof of concept in secure mode, because you have to have some sort of dynamic certificate creating and signing solution in order to create new certificates anytime a pod is given a different IP address than it had before. So this has worked really well for insecure deployments, and it's really fast and it's really easy to maintain. But setting it up for secure deployments is pretty tough. And so now we're getting to the thing that we actually have documented in our docs. And it's what I would call DNS chaining, which is a term I just made up. There might be a better word for it. But basically, we're taking that previous solution where pods are talking directly to each other on their IP addresses, which is great for performance. And we want to add some sort of persistent names to that solution. So we need some sort of persistent network addresses that will work even as the underlying pod's IP addresses change, because that will allow us to put those persistent addresses into the certificates for each pod. And then we can run in secure mode. And what we want to do here is somehow configure the built-in DNS server in each Kubernetes cluster to serve those DNS entries from the other cluster. But the question is how? Because kubedns is set up to only create DNS names for the services in its own cluster. One way to do this is to use core DNS instead of the default kubedns. So core DNS is a much more fully featured DNS server that allows for a lot more customization. It has a full plugin architecture. There's even an existing plugin called Kubernetes, which was written to allow one core DNS server to watch the API server of multiple Kubernetes clusters. So we could use that plugin to do exactly what we want. We could set up core DNS in each cluster to watch the services in all of our Kubernetes clusters. And then it would automatically create service names for the services in the other clusters. However, in practice, swapping core DNS in for kubedns on any of the managed Kubernetes offerings is very difficult. It's also difficult to modify each cluster's DNS domain. So you'll notice if you look at the full service addresses of Kubernetes services, they all end with .cluster.local, unless you've customized it yourself. And ideally, we would want each cluster to have a separate DNS domain, so it would be easier to distinguish between a service running in one cluster and a service running in another cluster, so that you don't hit naming conflicts between them. And that's also apparently very hard to do in the managed service offerings. I tried for a couple days to do either of these things, to swap to replace kubedns or to set up a different cluster DNS domain on GKE, and had no luck. We tried to do that earlier this year. However, core DNS is becoming the standard DNS server as of 1.13. So maybe this is going to get more feasible. Setting up a custom DNS domain might still be very difficult, so there would still be that roadblock. And unfortunately as well, the Kubernetes plugin that we would want to use doesn't come in the default core DNS Docker image that gets used. So it would still have some difficulties, but this is becoming more and more feasible over time as core DNS becomes the standard for Kubernetes. Another alternative, which I haven't fully explored, is to run core DNS alongside the default kubedns. So we could configure kubedns to defer certain lookups to core DNS, and then have our own core DNS that's configured exactly the way that we want it, running in each cluster, watching the other Kubernetes cluster. And we can use some of core DNS's plugins or the rewrite rules to make the cross-cluster lookups work out. But I haven't, fully tried this out, and I haven't heard of anyone else that's actually doing this. So if you're going to try this out, I think it, would work, but you're going to be in uncharted territory. So just be aware that, I don't think this is very well tread ground. Also, what we, to make this DNS chaining work, we could just take matters into our own hands. So instead of trying to use core DNS, we could just write our own controller that copies services from one cluster to another, and then they would automatically be populated in DNS. And since Kubernetes is just an API, anyone could do this if they wanted to. But it's much preferable to reuse existing solutions rather than build new ones, especially if I won't have a lot of time to dedicate to maintaining the new ones. So I haven't written anything like this. It seems like we should be able to use what's already out there rather than having to build something new. But this might be worth doing. It would be a great thing to contribute to the community if you do have some time on your hands to try it. What we've ended up doing for systems like GKE and DKS is using what are called stub domains. So stub domains are a kubedns config feature that allow you to defer DNS lookups for certain domains to the name server of your choice. So we can configure a suffix that allows the kubedns in one cluster to redirect lookups for anything that ends in that suffix to a different cluster's DNS service. So if you have a cluster in US West 1B and you do a lookup for some DNS address that ends in US East 1B.cluster.local, then kubedns will know to just send that along to the DNS server that's running in that US East 1B cluster. So this is what I put together some scripts for, and we've documented on our website for people to try out. And it's been most heavily tested on GKE. There are some great pros to this, right? So like the direct IP communication between pod solutions, there's no overhead on the data path other than that normal Docker overhead, which is tough to avoid. And it's very resilient to hosts being added and removed. There's no need to configure a cross-cluster naming service. You're just using the built-in DNS. And there's actually no or very little manual work needed to get this running. We have a script in the CockroachDB GitHub repository. You can just fill in a couple parameters on where your clusters are running and what their kubeconfig names are. And then you can just hit run on the script, and in a couple minutes you'll have a running multi-region Cockroach cluster. However, you need to have pod-to-pod communication across clusters for this to work. And you need to set up some way for the DNS server in one cluster to reliably reach the DNS cluster in another server. So you can do this using an internal load balancer on the various clouds, or you could use an external load balancer, or you could come up with your own solution for that. It's not great. On GCE, you today have to use an external load balancer because their internal load balancers don't work across regions. I believe they're working on fixing that, but I don't know when a solution will be around. And so that would be exposing your DNS server to the public internet, which probably has some serious security repercussions. You could put in some firewalls in place to keep that from being as much of an issue. But yeah, it's something to definitely be concerned about. You might end up needing to run your own load balancer to enable these DNS servers to find each other on the network. And at that point, maybe you should just use that load balancer to handle the pod-to-pod communication. Finally, Istio is a project that's become very, very popular in the community over the last year or two. And you could use it to basically handle the naming of services across Kubernetes clusters, or even the routing of packets across clusters. And they've been working on this multi-cluster mode to handle this problem of addressing across clusters for the last half year or so. It was in the very early days when I was doing most of my experimentation earlier this year. It explicitly punts on the problem of enabling pod-to-pod communication though. All it's doing right now is naming. And what you do is you install the Istio control plane in one primary Kubernetes cluster. Sorry for that K7S typo. And then you have to install this special Istio remote component in all of your other clusters. Well, I would say that while this is super promising, and hopefully it will solve the problem next year, as far as I can tell, it's still pretty far from being suitable for production use. And I don't know of anyone using it, Cockroach, to span clusters today. So it's under very active development, and it looks like it will improve quite a lot over time. And it has a very small overhead on the data path because packets go through the Envoy Proxy, which is a very efficient, low-level proxy written in C++ that's in use at a number of companies throughout the industry. And like past solutions, it's very resilient to hosts being added and removed. However, the cons here are pretty heavy right now. It's running the entire control plane in a single Kubernetes cluster. And so if that region goes down, then you've lost your connectivity between clusters. It still has a single point of failure, and that hasn't been resolved yet. The setup process is really involved. I really struggled getting it to work. It took a few tries to get everything working correctly. And they even say in the docs that even if you follow all the docs until the end, running a real production environment would require additional steps, at least one of which is solving this problem of addressing between clusters for the Istio components themselves. They have this problem where if the Istio components in the main cluster get like rescheduled onto different nodes and end up with different IP addresses, then those Istio remotes will not be able to reach them anymore. So you're actually just kind of like moving the problem from Cockroach into how you configure Istio. So it doesn't really solve things yet. And like some of these other, like the core DNS solutions previously, you have to copy the credentials for each Kubernetes cluster into the other clusters, such that Istio can talk to all the APIs. It's a potential security risk. As always, though, Kubernetes is open source. It's an open API. It's really, really easy to program against. So you can always do your own thing. Set up your own DNS servers, use pod IPs with some sort of automatic certificate approver that you write, use core DNS as you please, set up your own proxy servers, and so on and so forth. And there are definitely some good options here, but it's tough for us to widely recommend any of them due to differences between environments. So to summarize, multi-cluster networking is pretty tricky. It's much more complicated than I would have expected, or than most people would expect. And unfortunately, not a whole lot has been done about it for years. This past year is the first year I've seen a lot of good movement in the right direction. And even after you nail pod-to-pod connectivity, so after you solve that first networking problem, you still have to solve the problem of providing stable names that work across clusters. But I am really excited about these different projects that have spun up that are starting to care about it, though. So you have the Cilium overlay network, which has the cluster mesh mode. You have Istio trying to solve the naming problem. And there are even companies like Upbound, which just released the cross-plane open source project, which is supposed to help you run applications across multiple clouds using Kubernetes. So it's hard to recommend a single answer for everyone. But out of these few solutions, there's definitely at least one of them which would be very reliable for you if you're willing to spend some time up front and set up. So thank you for tuning in for this webinar. If you have any more questions, I'll be answering some questions afterwards. And you can always find more information on our website or on our GitHub repository, or reach out to me via email or Twitter. So I'd be happy to take some questions now if anyone.
Okay, thank you everyone for joining. That wraps up the webinar today. And we just had a few final quick announcements.
Yeah, so I just wanted to provide a couple updates since Alex did that talk. Core DNS is now the default DNS resolver for Kubernetes 1.14, 1.15, and 1.16. However, if you're using Google Kubernetes Engine, you will still be on kubedns by default, even with a more recent Kubernetes version. Fortunately, if you go to the core DNS repo, there is some very easy instructions for how you can replace kubedns with core DNS on GKE if you're interested in that. And so using core DNS with subdomains is how we have implemented multi-region Kubernetes within the CockroachCloud team at the moment. Also, the Istio project has become a lot more mature in the past year. And so you can now actually run the Istio control plane across multiple Kubernetes clusters rather than having a single cluster being the leader. So I definitely recommend trying out Istio as well. I also want to mention that we're giving a talk at KubeCon Rejects this Saturday. So if you're going to be there, please check it out.
And then we'll be at KubeCon as well next week. And we're doing this cool initiative where if you come by our booth and meet us, we're going to donate $5 to Women Who Code for every lead scan we get. So it's just a great way to give back to the community. We're really excited about this initiative particularly. So hope to see you there. And thanks again for joining us. Yeah, that's it. See you guys later.